Great. Hi, everyone. Great to be here. I'm a big fan of PyPSA, though I've always felt a little technically challenged to contribute. But this may be more a curiosity for people. I work at a company in India called Serentica Renewables, which builds wind, solar storage assets on the large scale. So how we use PyPSA as one of the tools to make our investment decisions is a little bit different to maybe the median PyPSA user who's looking at countrywide energy studies and things like that. Here we use it to look at the asset level and make some of our decisions there. So yeah, hope it's interesting. So just a bit of a as mentioned. So Serentica is a traditional what you might call a developer or a independent power producer. We have about 3 gigawatts of wind, solar, and battery storage across India, which we build, own, and operate. Yeah, that's about, oh, sorry, 2 gigawatts and a lot more under construction and in the pipeline. So, one difference maybe from traditional utilities in other parts of the world is that Serentica mostly works on what's called round the clock PPAs, or you might be familiar with 24/7 clean firm energy. Basically, PPAs where there is a requirement for the developer to combine multiple clean sources, maybe overbuild, and take on some of the risk of shortfalls of meeting the PPA requirements, and also the managing the excess energy produced. And so we need to do a lot more modeling than, say, just a simple annual generation figure. So tools like PyPSA are really helpful for this. Um, and generally, we're looking at, say, individual groups of plants, so on the assets and at a higher time resolution. So um, that why we use PyPSA or and other tools. We also use, say, Plexos for some purposes. Users would know they're pretty interchangeable. Um, Basically, if someone asks you to provide a firm power requirement, there's a lot of options. How much storage, how much wind, how much PV, how much can you buy from the market? Uh, just even pricing it. You need to be able to simulate to the sub-hourly level the interaction of different sources and be able to run a lot of different scenarios, which PyPSA is great for. So just a bit of an intro into what are round the clock PPAs. Um, as mentioned, say if the on the left in this table is the base most traditional PPA or power purchase agreement contract, which is basically whatever I produce, you need to buy. So a traditional run of plant, they offtake and there's no risk on the developer. If we go to the round the clock, then there's a whole number of different ways you can structure PPAs to be round the clock. Currently, with just wind, solar, and storage, it's not easy to give, say, 100% whenever you need power, we'll give it to you. Generally, or at least it's very expensive to do so. So there's a lot of different options are all considered round the clock. It may be, say, okay, a flat demand profile of 100 megawatts, you need to give 55% over the year. Or maybe it's to that flat demand, we'll add some peak hours where you need to every day provide, say, 90% of that. Or maybe it's not a flat demand profile. It's a if you can look ahead and say sculpt your demand seasonally and daily, then we'll only offtake the power that there. And even we've done projects where there's even say every 15 minutes you need to provide a certain percentage of power. So that's like definitely a big proportion of that ends up being, say, base load. Um, and so for that you need a much more complex mix of assets to be able to provide that. Here's just I did a bit of an illustration. So on the left, you have, say, the annual generation of a wind solar storage plant of a certain capacity, um, just showing the average annual generation for each hour by technology. And here, the dotted line you might see, laser pointer. Here, this would be, say, if we have a 100 megawatt PPA, anything above this 100 megawatts would be have to be to the account of the power producer. Would sell that be excess or curtailed or sold somewhere else. Um, but and say if there's a penalty of 70%, the area under the curve averaged over the year has to be fulfilled here, and any gap would be would cause penalties. And so then moving to the next one, so say this is the same generation profile, but here if this would be a load following, then the amount of power which they offtake would change, say by hours a day if they're doing it here, but it could also be by say month of the year. Um, this shows, if they're not taking very much power during the day, then you either need a lot less solar or a lot less a lot more batteries, something like that. You need a different configuration for it to work best. So that's just a bit of a graphical illustration. Um, so then how do you solve these problems? If a customer comes and says, okay, our load profile looks like this, or even if we want to go to a customer which already has a lot of solar in the day, for example, how do we design something which will meet their requirements? So the answer is always you model it. You model all the different scenarios. So um, in PyPSA, you can just basically set up a mini network, um, which here is not really reflecting the grid. It's more reflecting the contractual flows of power here. Um, so this could very much reflect the physical assets to some extent. You have, say, wind sites, PV and BESS sites, etc. But then because you're, say, selling over the national grid, you would then have abstractions to say, okay, so at our point of power delivery where it connects into the grid, then you want to model the contractual flows. So what is the power which will be, say, injected into the grid, and then the customer will take to their account. Um, and then you may have some interactions with, say, the buying from the grid market. You could replicate that with a generator, and similarly, selling excess to the market. You could replicate that with a negative generator. And then because PyPSA doesn't say have the ability to specify exact penalties, things like your allowed shortfall and your penalties can be modeled with generators as well. And you can, as we all know, we can use pretty cool LinearPy constraints modeling to make sure that everything works, to model all of that. So yeah, what's some of our learnings here? This is a lightning talk after all. I guess basically PyPSA is definitely a really useful tool for commercial developers. Um, and it's useful for modeling, say, assets now. I think this is going to be something which all utilities and developers will have to work with to some extent, because even just say modeling batteries and modeling the interactions across your portfolio, you need tools which can really build in these contractual and sometimes constraints, um, and work across a number of assets. So Pipes is really good for this because the constraint modeling is super flexible, and I've never found something that I haven't been able to model yet. Some learnings, I think, for anyone who wants to do, say, asset level simulations, um, the inputs are really important. If you want to do asset modeling, then you kind of have to look away from, say, error 5 or high level simulations. I would suggest if you can get historic generation of actual operating plans, that will be very insightful, even if it's maybe not, perfect for your location. And for users, I'm not a how do you say I didn't know how to use Python or coding before using PyPSA. Um, so it was really easy to learn. But one of the ways we've made it more accessible is, say, setting up Excel workbook templates for network creation, and for bulk running networks and changing scenarios. It's very easy to say set up an Excel workbook which you can ingest into standardized boilerplate pipes of code. Um, there's a branch or a package called Tables Pipesa which can give some inspiration, but it's pretty easy to make your own. And yeah, yes, and the last one we found is that even if you don't have a commercial solver, you can still run a lot of different studies even without doing capacity expansion models, just simply by, say, running many different ST runs. Um, and then by using parallel processing, you can really run a lot of these very quickly, sometimes faster than you may just by doing LT runs. And the good thing about that is then you can really see your options and the trade-offs rather than just having to take the lowest cost solution. Though the new modeling with alternatives to generate alternatives is another way to do that too, which I'm looking forward to get exploring. But great, that's all from my side. Any questions?
Thank you, Matthew, for the presentation. Yes, we have some questions. Actually, I forgot to mention it before your presentation started, but for every presentation in the chat, you will find a link to submit all your questions. So you can just copy the link and paste it in your browser to ask questions to our speakers. So one question that we have here is for modeling RTC PPA scenarios, PyPSA was used or PyPSA Earth?
Yes, yeah. This is I should say this is PyPSA. Yep.
Okay, great. Thank you. Then we have another question. Are there sample notebooks of the studies?
Um, Sample notebooks. Yeah, I've been meaning to give back to the network. Sorry, to the community. I'll do my best. It's always difficult. Representing company as well. But definitely see what I can do. Yeah.
Uh, Yeah, thank you, Matthew. Yeah, maybe if you have anything after the meeting today you want to share it, we can definitely circulate whatever supplementary material you have with all the people participating to the meeting. Then I will make you have will maybe make a summary of the two questions that I see here. So but I think you answered it already. So is there any open repository where the work can be accessed, and how can we get the data if we want to replicate what you presented?
Yeah, I mean, I didn't present much in terms of studies. This is more a sample, but basically, it's just the idea that you can model the interaction or commercial interaction of hybrid plants, and I'm sure many developers and will look to do so. But yeah, it's fairly simple to set up networks, which basically represent, say, a small proportion of a portfolio or a hybrid plant itself. Um, yeah. Okay, let me see. Commercial tools. Yeah, we use a big range of commercial tools. We use both of them. Um, and looked at many open source tools as well. Pipes is my favorite open source tool. Um, from my experience, which is better, Excel sheets or pipes of modeling? Um, so with Excel, you cannot model, say, dispatch decisions, optimize dispatch decisions in the same way. You need to use linear optimization, which is why you need a tool like, say, PyPSA. For the PA agreements, required. No, they don't really mind. At the end of the day, it's a legal contract. How you get to the price or the legal contract behind there is up to you. Commercial tools. Again, yeah, this is for our own use, I guess. Yeah. Um, it's just another tool, which there's a lot of it's like if you build a financial model with Google Sheets instead of Excel. I mean, well, that would be blasphemy for a lot of companies, but yeah.
Okay, thank you, Matthew, for for actually also going through the questions and for your answers. Thank you again. Of course, if I see another question, I think we still have time for that, so maybe we can also answer this. Um, maybe, yeah, maybe that was not a question, but maybe this is interesting. How did you incorporate penalty in the objective function?
Yeah, sure. So, yeah, that's the main difference, I think, between using pipes. So where you're talking about a grid which needs to be balanced, and so that to meet that balance is actual flows of electrons. Whereas if you're modeling, say, just a group of plants which are connecting to a grid, um, you don't have that balance requirement, right? We're not A renewable plant doesn't have to make sure that it's meeting 100% of the load all of the time. So how you do that is by modeling, say, having generators to model this. Um, so and then constraining those generators. So you may have a free generator. Say if you only need to meet 55% over the year, you have a free generator which in all the 45% hours can generate freely to make up the gap so that you have a balance. But then you would just constrain it so that it cannot do more than say 45%. And then you would have a penalty generator, which would then basically have a higher marginal cost of power, and it would only come into play when the free shortfall generator is not able to generate due to those constraints. And so and because that penalty generator has a higher cost, you're accurately modeling the flows. Offtake constraints, yeah, it's very flexible, I would say. You can basically put in any profiles of load and any profiles of supply, and yeah, with LinaPy you can do everything. I would say it used to be a lot harder to come up with some of those constraints. Now with AI, it's really amazing how accessible LinaPy has become.